All right, last time we finished with this function, right? The int sum1. And this was getting a, sum all the numbers from 0 up to and including n, and then return the result. So if I put in 5, I want it to be 1 plus 2 plus 3 plus 4 plus 5. And the way I've written it here is I've got a variable called running total. That's going to keep track of the running total. After that, I've got counter and starting at 0. In this particular example, the variable counter is serving two purposes. One, it's keeping track of how many times the loop has run, right? We only want to run it for 0, 1, 2, 3, 4, 5. But it also will be holding the current, integer, right? So, the first time through the loop, counter is 0. Whatever, 0 is not interesting. The next time through the loop, counter will be 1. And I want to add 1 to my running total. Next time through the loop, counter will be 2. And I want to add 2 to my running total as well. And so on, same all the way up to 5. Counter will be 5. I also want to add 5 to my running total. So it's kind of serving two roles there. But what I wanted to show you yesterday was, so I have this less than or equal to n here, because I want to make sure I'm including it. But I can do a quick little switch. I wouldn't write it this way, but this should also work. So the switch is, I made it strictly less than. It's not less than or equal to. And I changed the order of how I'm modifying the counter and running total variables. Does this switch make sense? The difference here is the first time through the loop, counter is 0. It's true that it's less than n. I immediately add 1 to counter. So it becomes 1 before I add anything to the running total. So where before I was adding 0 to the running total, which is useless, here I just enter the loop when counter is 0 and immediately make it 1 before I use it to add anything to my running total. So here, let's say counter is 4. Counter is 4. Is 4 less than n? N is 5. Yeah. So we go into the loop, immediately add 1 to counter, it's 5. Then we add the counter to the running total. So this will also work. Just slightly changing the order of steps can have a little bit of a different effect on how it needs to be coded up. Any questions on that? All right, so an algorithm. Everything we've written so far, all the functions have been algorithms. There's no ifs, ands, or buts about that. All an algorithm is a series of instructions, like steps you would take that would help you achieve something. Make sure your masks are on. So it helps you achieve something. Honestly, baking a cake, like following a recipe is an algorithm. I'm not being silly with my terminology here. It is. By definition, it's an algorithm. We don't really think of them as algorithms. We think of them as, well, a recipe. But same with driving instructions. The steps you follow to get from point A to point B, it's an algorithm. But you probably never really thought of it as an algorithm. We're doing the same thing here with our code, is we are setting out the steps one by one on how the computer's supposed to do its thing, and it'll solve the problem in the end. If you're looking for your mask, it's on your neck, I think. Isn't it?
Oh, no, that's fine.
Never mind. So algorithms can be explained in natural language like English, like recipes, or driving instructions, like, oh, drive all the way down Hawthorne, turn right once you get to whatever, We could explain algorithms with human language, like in English, but we can also write it in code, like Python. Finding it out, like writing algorithms, is a huge part of programming. Like it's all of what you're going to do, but it's kind of interesting because there are certain problems that we want to solve, so we write algorithms to solve those problems, right? So the algorithm is hopefully the solution to solving the problem. But there are some problems out there that we currently don't have good algorithms for. And we don't actually know, and when I say like we don't, I mean like scientifically, mathematically, we don't know if the reason we don't have a better algorithm for solving a specific problem, we don't know if it's because one doesn't exist, like we're just stuck with it, or have we just not found it yet? We don't know, which is kind of interesting. Here's an example of a problem that has a very simple solution, but it's hairy. Imagine I told you, see how well. There. Pretend all of these dots are cities. And your job is, you're a salesperson. Your job is you start here. Okay? What you have to do is you need to visit every city. Like you could get from this city to any other city. You need to visit every city exactly once, and you need to start and end in the same city. But, you know, if you're putting your brain, like if your spatial reasoning brain on, there's going to be better paths you can take than others in terms of, you know, reducing the total amount of traveling you're doing, right? What I mean is, you wouldn't go from here to here, back to here, all the way to here, then to here, then to here. Like there's a lot of backtracking involved. That would be all over the place. A more reasonable thing would be something probably like, I don't know if this is the best, but, right? The green marker didn't really work at all. Let's try that again. Only a little bit better. Right, there's going to be good paths and not so good paths, right? All paths are valid, but we want to minimize the total distance we've traveled. So if I ask, here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's add another one to have a nice even 10. 10. Let's say that I added a 10th city, so all these paths are terrible because we missed one. But let's say I have 10 cities. And you have to visit each one. Okay, so we would want to write an algorithm to solve this problem. What I'm looking for is, what is the fastest route? Such that you start at the X, you end at the X, and you visit every city once and only once on your path. So what is an algorithm for this? Well, here's a simple algorithm that I'm just going to explain to you in English. Why don't you just try all possible paths? Well, trying every path, calculate the total distance traveled. And then once you've tried all the paths, just pick the path with the smallest distance. Does that seem reasonable? It should, right? Just try every possible path, see how long each of them are, and then if you want to minimize it, just pick the one with the smallest distance. Great. Here's the problem. One, that algorithm, easy to do, that algorithm is correct. It's provably correct. It will absolutely guarantee that you'll find the best solution. Right? Try every one, pick the best one. Done. Great. It's correct. Where the problem arises is, well, how many possible solutions are there? Right? How many possible paths are there? I could get a little fancier, but think of it this way. Let's say I have 10 cities, okay? I'm starting here. How many options do I have from here? How many other cities could I visit from here? 9. Okay, so let's say I visited this one. I mean, right now we're thinking, okay, we could visit any of these 9 from here. And then after we've picked our second city, the city that we're going to go to next, how many options do we have left?
8.
Then how many?
7.
Then how many?
6.
Then how many?
5.
So there's 10 cities. So the first city's fixed, so we don't really need to worry about that. But I have 9 options. Okay, so from the 10 cities, I have 9 options. And of each of those 9 options, how many options do I have following it? Well, it was 8. So we have 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So have we seen that before? What's it called? Factorial, which we just learned about. So that's actually factorial. What I would say is, for ease, because computer scientists are lazy, I would say, well, the number of possible solutions here, the number of possible paths here is on the order of 10 factorial. On the order of n factorial, where n is the number of cities. Okay? So that's what I would say. So if I needed to write a program to try every possible path, I know how many paths it would need to check. So let's do a quick look here. How many possible, so if I want to get fancy, really it's n minus 1 factorial divided by 2. N minus 1 because, well, the 10th city's fixed, so you don't need to worry about that. Then it's divided by 2 because you figure, well, for one city that says, like, go to city A, then B, then C, then D, you would have a path that says D, C, B, A, so you don't need forwards and backwards. But for simple math, I'm just going to do factorial. So if I had 10 cities, how many possible paths does my computer need to check? 3,628,800. That's not too bad, right? But that's only 10 cities. How many paths would I need to check if there were 100 cities, right? What do we got? Oh boy. 9.33 times 10 to the 157. There's 157 zeros. The algorithm to find the shortest path is simple. It's guaranteed to work. The trouble is, I'm not joking when I say, there are more possible paths between 100 cities than there are atoms in the universe. That's not a joke. You could take every single atom in the universe and assign one of the paths of 100 cities to each one, and you would run out of atoms really quickly. How many atoms are there in the universe? Let's find out. How many atoms in the universe? Times 10 to the 82. We are orders of magnitude. We are like what, 82 to 150? So like we are like more than 70 times, like we would need a lot more universes. Isn't that crazy? There's more possible paths between 100 cities than there are particles in the universe. It's nuts. The problem with this algorithm is it'll work, but good luck. Like you're not going to be able to run this on any computer and have it finish computing before the universe dies. It's not going to happen. So we've got a problem, don't we? There are some problems out there where, is there a better algorithm? Is there a better program I could write to find the optimal solution than what I have? And there are definitely improvements. But is that the best? Are they computationally tractable, is the word I would use? Is it reasonable to run that algorithm to find the solution? That's where things get weird. But let's get back to more concrete stuff. So, talk amongst yourselves. And all I want you to do is, so here, let me go back to the other solution, because I find it a little bit more intuitive. This is an algorithm for summing all of the integers between 0 and n inclusively. But I want you to modify this algorithm to just give you the sum of all even numbers. And here's what I want you to do. I want you to talk among yourselves and explain in English how you would do it. I mean, this is your starting point. If I'm going to explain this algorithm to you in English, here's what I would say. Is, okay, well, I'm just going to have a loop that counts 1, 2, 3, 4, 5, all the way up to n. And every time through the loop, I'm just going to add the current counter value to the running total. That's it. If I ever ask you to explain an algorithm and you start going like, well, make a variable called running total, set it to 0, make a variable called counter equals set it to 0, and then we check, wow, counter is less than equal to, no, that's bad. I don't want you to just read me what's literally already written. That doesn't make any sense. You just explain, like imagine what the doc string would be. Obviously, it's a little bit more detailed because we're explaining how the algorithm's working. But I would explain this algorithm by saying just do a loop. Each time through the loop, add the loop's counter to some running total, and then we're done. Like, that's the algorithm. So how would you take that as a starting point, but modify it such that you're actually only getting the sum of all even numbers between 0 and n inclusively? Take a moment to talk amongst yourselves. See if you can kind of like explain it intuitively with English. And then after you've spent some time doing that, see if you can code it up. I don't want you to just go straight to the code. That's kind of defeating the purpose of this exercise. Anyone have a solution yet? Who here will totally have one if they have just one more minute? One person? All right. I'll still give you the minute. So to me, if I'm going to think of this algorithm in English, I would say, all right, so the starting point is what we have here. It's, okay, have a loop, start at 0, go up to n inclusively, and every time through the loop, just add the current value of the counter to the running total. But I would modify that a little bit here for the only when they're even, to just be like, well, okay, we've got the loop, and we loop, and we have the value of the counter as we go, but we only want to add to the running total if the number's even. Right? That's the catch. There is loop over, like, all the numbers between 0 and n, and add the value to the running total if it's even. So all we have to do is check if the number is even. Anyone remember how we do that easy? Yeah, a couple people shouted it out. We do that mod 2 thing. Remember, mod is division, but it's only the remainder. And if you divide something by 2, and it has no remainder, it must be evenly divisible by 2. So all we have to do is, while that, if counter mod 2 is 0, we add to running total. Regardless of if we're adding to running total, we still need to increment counter, right? The counter still has to go. It's only the adding to the running total that has the condition on it. So if I type in 5, what should the result be? It should be 2 and 4, 6, right? 6, nice, cool. Any questions about this or how I thought about it or anything? Yes.
How come you couldn't just take the original function, just turn the counter plus equals 1 into plus equals 2?
That would totally work, wouldn't it?
Yeah.
So his solution is, well, instead of having the if condition, just count by 2s. Looks like that would work as well. Who here did it this way? 2 people. Who here did it the other way? 3, 4 people. Both would work. And look at that. 2 kind of quite different approaches to solving the problem. I mean, it's got the same framework. We're using the loop. But one, we checked if the number's even. The other is just count by 2s. Both are entirely valid solutions, which is great. By the way, assignment 2 is posted in its entirety, I think. Just make sure everything looks like it's, oh no, did something not format right? Oh no, it did. Looks scary, eh? It's got about zombies, so it is scary. Ooh. All right, cool. All right, strings. I'm going to talk a little bit about strings. Now, of course, we're already well aware of strings, right? Strings are just one of the other types we were used to. We had our strings, or our integers, floats. We learned about booleans. We learned about the none type. But strings are kind of funny, aren't they? Because strings, like when I have the number 14, like the number 14 is represented by a 1 and a 4, but really that 1, 4 means a single thing. It means the value of 14, right? So the integer, if I have something of type integer, that integer variable is holding one number. Similarly with floats. similarly with a Boolean. It's holding either a true or a false. But strings are funny because a string kind of has a lot of information in it, right? A string could be the letter A, or it could be or it could be a string of A. So the funny thing about computers, with how these things are designed, these computing machines here, is, and I'm going to simplify the idea, but you know, all of the information we're storing in our computer needs to be stored in the computer somewhere. And for that, we're going to use RAM, random access memory. And RAM is broken down into like nice divisible slots. Okay? And if I have an integer, I know how much room the integer that I want to store, I know how much room it takes up in RAM. I would just put my integer in one of these seats, right here, right? And the integer is happy to sit there. Every integer I can have is going to fit in that seat. Okay? It fits nicely. Same with a Boolean. A Boolean I can shove in this seat. I don't know how big it is. It doesn't need to take up a lot of room. Same with a float. Same with a numpad. They fit nicely into that seat. But the problem is, if I have a single letter A, well, you can think to yourself that an A would very gladly sit right here. But what happens if I have the string AA? Can I really shove two A's into one seat? Or what if it's A? Can I really shove that all into one spot? We're in a little bit of a pickle. Because I know how big every integer is going to be. In terms of big, not in terms of the value of the integer, but I know how many seats, how much square footage of RAM that integer can take up in my computer. I know. If you make a variable that's an integer, I don't care what value it is, I know it can fit in one of those seats. I'm happy with that. But if you make a variable that's a string, the computer's got trouble because, well, how much room does that string take up? How big is that string? The bigger the string, the more room it's going to need, right? Strings are kind of funny. They're a little peculiar. They're a little different when compared to our integers, floats, and whatnot. One thing is, well, you know, a string really is actually just like a series or a string of individual characters. Right? That's all it is. In fact, like we saw in Caddis when we were like playing with import or input, when we could like index lists, you can actually index individual characters out of your string. Like right here, for example, I have a string called hello world. If I say, give me some string at index 0, it'll give me the letter H, the thing at index 0 of that string. Remember, computer scientists start counting at 0. If I wanted the thing at index 4, I would get, well, 0, 1, 2, 3, 4. I'd get the letter O. If I wanted the thing at index 5, I'd get the comma. The thing at index 6, I would get a space character. The string is actually made up of a series of individual characters, which is really interesting. Because an integer is not made up of a series of different, it's just a value. Where a string, it's a little, there's like more information there. Would you agree? Yeah? So, in Python, yeah, okay, that's the 0 thing. So, you know what? With this in mind, do this activity. I'll give you a couple minutes to this activity. Write a single line command to print the first 4 letters of some string. A single line command. It doesn't have to be single line. Just do whatever you want. Just play around with this a little bit. You know what, for the sake of time, I'll just show you some of these ones. we go up here, copy this. There, I get the H and the O. Now I was saying do it in a single line, didn't need to do that. But I could just keep indexing these things. There. What do you think if I were to index it at index 77? What do you think will happen? Give me the thing at index 77.
Guess it'll loop around 77 times.
Guess not. String index out of range. It could have gone either way. This is more of a how is Python designed. So here, it's just saying there is no index 77. What are you asking me to do here? Right? So there is a limit. And kind of an interesting thing, this is more of a Python thing. You're not going to see this in many programming languages. You can do negative indexes. That'll just actually just count backwards. So when I put in -1, it actually gave me this. Which is kind of cool. -3 should get me the L. Yeah. 1, 2, 3. That's kind of cool. There's also something called string slicing, where you can say 0:4. Oops. Where it just says, give me everything from 0 up to and excluding 4. Usually in like code, whenever we have like a conventional, it'll always be like including 0 up to and excluding the high limit. Yes?
So when you're going from left to right, it starts at 0, but when you're going from right to left, it starts at -1?
Yes, but remember it's still, this is 0, but -1 from 0 is here. You're right that it is kind of funny, but you still think of this as 0. Yeah. So this is called slicing. So this gives me, if I do 2 to 7, we see LLO. So 2 would be 0, 1, 2. So we get the L, 2, 3, 4, 5, 6, but we exclude the 7. Let's put an 8 in here so we can see the W, but it won't include the 8th character. So that's called slicing. If you like it, great. If you don't like it, you never need to use it. It's just a cool little thing you can do in Python. If you want to get really fancy, you can actually add a third thing here that tells you how to count. So if I count by 2s, it'll skip every other one, but whatever. I'm just showing you interesting trivia at this point. The important part here is you can index these letters. Now, if you're thinking, I can get information from a specific index of that string. Can I change what's at that index in the string? What I mean is, if I say, okay, some string in index 1 is an E. It's that E. Could I do something like this? Could I say, equals X or something? So can I say, no. I don't just want, like we saw we could retrieve the information from a specific index. Can I go in and change the value at that index? Because if I'm using it kind of just like a variable, I get information out of the variable. Can I change the value of that variable by indexing? See what happens? No. This won't work. Of a consequence of how strings work inside these computing machines. Strings are what we call immutable. It means you can't change it. Just think of it like you have a TV with a mute button, but it doesn't work. I can't make it stop. I can't change it. I can't hit mute. It's immutable. Okay? So strings are immutable. Things that we can change are called, who wants to guess? Mutable. Yeah. So you can say it with more conviction next time, though. Your answers were like, mutable? Yes, it's mutable. So there are some types of information that maybe we can go and kind of modify facts about the data. And then there are some things that are immutable, like the strings. Once you create the string, that's it. I can change what the variable holding the string has. I'll show you what I mean. I can say some string equals not hello world. And if I print out index 0, I get the O. So I can change what the variable is, but it's kind of funny, because right here, this is the string. The variable some string isn't the string. The variable some string has, like in its body, it's more complex than this, which we talk about shortly in a couple of topics. But the variable just has like the reference to that value. I can change what the variable's referencing. I can say, no, some string, you now have not hello world there. Great. But I can't go in and change information within this string. Like I was showing you, I can't say equals 6. Because this would be saying, okay, go into that string and change something about it. It's a subtle nuance at this stage what the difference is. But maybe I can draw it a little bit. If I have a variable, and here's the string, right? In my variable, this is st for some string, right? I can go and say, okay, you've got like that value. And then I can just say, okay, just some arbitrary other string, and I go, no, okay. So now you've got this value here. It's what the variable's referencing. When I do something like index the string, like on the last line there, on line 4, where I say print some string at index 1, what the computer's going to do is go, okay, some string at index, 0, 1. I get this n. But on line 3, where I'm trying to set what some string at index 1 is, that would be like saying, okay, index 1, and then I don't want you to be n anymore. I want you to be a big X or something. That's not allowed. I cannot modify this. The value and the variable are separate. There is a lot of value also in having immutable data, because if you know it can't change, you know more about it, like it can't sneak up on you and get changed somewhere, but that's a thing you'll get an appreciation for at the latter half of the course. Any questions about that funny little nuanced difference there? We're going to hit this difference a lot harder in like 2 topics. Yeah?
This is kind of like what you were talking about earlier, but why is it harder for the computer to store like 20 character string versus 20 integer or digit integer?
Say that again?
Why is it harder for the computer to store a 20 character string than a 20
because the digits, the string hello is the string HELLO. That's what it is. Now, if I have the number 1, 2, 3, 4, 5, like 1, 2, 1, 1 followed by 20 zeros, right? That's a lot. There's 21 different things there. But the number isn't 21 digits long, really. Like, it has a single value, right? So the number is a representation of a value, one, like, single thing. I can get a little bit more detailed, and we will in, like, 2 talks, but I'll just go over it right now. Let's say, classically speaking, I've got a 32-bit computer, meaning I have 32 zeros and ones that my computer is happy, like indexing and doing all this other fancy thing. Long story short, I have 32 zeros and ones, because it's binary, that I can use to store a single integer. And with only 32 bits, I'm actually capped at like a couple billion in terms of the values I can have. And there's ways around that. But I know how big any integer could be because each integer is allocated 32 bits that it could have. It could be the integer 0, but that integer 0 is going to be represented by 32 zeros. It could be the integer 1, it'll be represented by 1 and the 31 zeros. And so on and so on and so on. It could be all ones, too. Either way, it's always going to be 32 bits. So I'm going to break my computer memory down into 32 bits. Again, this is a very simplified version of thinking about it. So I know that that's where it's going to fit, right? It could be a 0 or it could be 2 billion. It's going to fit in that block. It's going to be the same thing with a single character. How big is a single character? Well, I have 32 bits that I can use to represent a single character. Each character, each letter, can fit in one of these seats. But if I have a string of 5 letters, I need 5 seats now. It's because I've broken my computer memory down into these nice little bite-sized bits, where I'm going to put individual values into each thing. Did that help explain it?
Yeah.
I think in 2 topics, when we get to referencing and whatnot, this will come together a lot nicer. Other questions? It's a good question, though. Okay. All right. For loops. Raise your hand if you've seen a for loop before. Put up your hand. It's an assignment. For crying out loud. For loop. So a for loop is a handy special type of loop. The way we use for loops in Python is more analogous to like a for each loop in many other programming languages. But a for loop is a way of saying, like, okay, here. I think this is best described with an example. Vertical print while. This is a function that takes a string, and what it's going to do is print out each index, or pardon me, each character in the string, from the string, on its own line. That's what this code is doing. So I'm just going to copy it. Get rid of the doc string just for the sake of space. There. So what happens? Vertical print while, okay, character index starts at 0. Well, character index is less than the length of the string. You can do this, by the way. You can say, how many characters long is this? So is 0 less than 1, 2, 3, 4, 5? Is 0 less than 5? Yeah. All right, print out a string at index 0, increment character index. Character index is 1. Is 1 less than 5? Yeah, print out the next one, so on and so on and so on. Now this might startle you a little bit because you might be thinking to yourself, why is it not less than or equal to the length of the string, right? There's 5 characters. But remember, a string with 5 characters, a string that has length 5, has indices 0, 1, 2, 3, 4. Right? There is no index 5 in a string that's length 5 because we've got that 0. So that's why the less than here works nicely. Any questions at all about this function? It's just a loop. We're going to loop from 0 to however long the string is, and we're going to use the counter in the loop to be the index each time to the loop. So it'll index character index 0, then index 1, index 2, index 3, and so on. So we get hello. This is, of course, with a while loop. Whatever. The while loop works perfectly fine. There is nothing wrong with the while loop. But there is another type of loop called a for loop. Because there's a little bit of overhead. with this for loop. Overhead being, okay, we need like a counter variable, we need to check the condition, and then we need to increment the counter variable for our while loop. A for loop is a way to loop over each thing in a collection of things. So I can modify, here's what I mean. I can modify this, I can try to modify it, call it vertical print for, I don't want this, I don't want any of this. What I'm going to do is I'm going to say for in a string print character. Oh, and then I guess I'm going to call there. So this is a much like cleaner, for lack of a better term. There's a lot less boilerplate code we need. We don't need the counter, we don't need to increment the counter, we don't need to check condition on the while. This syntax, what it means is, for each thing in the collection of things. Now, in our case, it's each character in the string, because the string is a collection of characters. But for loops can be used more generally, like you've seen in assignment 1. In assignment 1, there's a for loop used to iterate over each location, each Starbucks location. So in that case, it's going to be each lat long tuple in the collection, the list of latitude, longitude tuples for each Starbucks location. Now, the thing, so for character, that thing I wrote there, character, I called it character. This is just, I'm creating a variable here that I'm going to put each thing in every time in the loop. I could call this if I wanted. It doesn't matter. This is just, okay, for each thing, and every time through the loop, the current thing is going to be stored in that. I called it character because, well, I know it's a character. This is the string, the thing I want to loop over. So the first time through the loop, the first thing in the list, or pardon me, the thing at the beginning of the string is a W, so we see the W. Then it's an O, we see an O, then R, R, L, L, D, D. So using the for loop, it allows us to iterate over a collection without a lot of that overhead of the counter, checking the condition for the while, making sure we increment the counter, all that. It's just a little bit of a different way to do the same thing. So here's right there. This is me just saying it really doesn't matter what you call this. It's just a variable name that is used to hold on to the current thing. All right, and we'll stop here.